Hey y'all, so we're going to go through an example today that's going to include both your Newton's second law, so forces, and kinematics, all right? Now what you're going to find is that as we get deeper and deeper into our physics is that a lot of these concepts will overlap, right? There'll be a lot of questions that require to use dynamics, forces, and kinematics, and energy and momentum, right? And so all of these things are very interconnected. That's kind of the whole point, is that everything connects to each other and we can use bits and pieces of information to put them together to come up with a conclusion. The more that we know, the better the ability that we have to combine ideas, the better that we can create that conclusion, that prediction, right, of what will happen in the future, or maybe of what happened in the past, why something is happening now. So here we go. We have a block sliding down a smooth plane having an inclination of 15 degrees. The block starts from rest and the length is 2 meters. So the first thing I'm going to do before I do anything else is I'm going to go ahead and draw a picture because that's usually a good idea. So we have my angle of 15 degrees. So that's the ground right there. Okay. The block is on here. It starts at the top, starts at rest, so I know my initial velocity equals 0, both horizontal and vertical, right? It's going to slide down this smooth plane. I want to point that out. When they say smooth, that means no friction. All right, so if you see smooth plane, generally that means that we're considering that there is no friction in the situation. If you see a rough plane, then that usually means that it's rough, therefore there is friction, all right? But that's one of those things where they won't clearly come out and say it, but in this situation they just say a smooth plane. It does say that the length of the ramp is 2 meters, and so therefore from here down to the bottom, that's 2 meters, all right? Now, at this point, the first thing that it wants me to do is to find the acceleration of the block. Now, we've used acceleration with both kinematics and with forces. And so it may seem that either one of those should be okay here. I want to show you first. Let's see, well, I'm really familiar with, I really like my kinematics. So let me see if I can use kinematics, all right? Now, the first thing I am going to do is I am going to tilt my x-axis. You'll remember that we talked about in class, our x-axis normally goes like this, but when we're on a ramp, we very often tilt it so that our x-axis is parallel to the slope. That will often simplify things, not just with forces, but with kinematics as well. And so we're going to go ahead and put my x-axis here, all right? And then my y-axis will be perpendicular to that. All right, so we've got our x and y axes here. You'll notice that because I made my x-axis parallel to the ramp, that therefore the block will slide in the x direction. And so therefore, if I start looking at my kinematics, then I would go x naught, x, v naught, v, a, and t. With that, I know the initial position. I start up at the top, which is 0. I know the final position, which would be x equals 2 meters. I know the initial velocity, which is 0. I don't know the final velocity. I don't know the acceleration. That's actually what I'm looking for. And then I don't know the time yet, all right? Now, with that information, do I have enough that will allow me to use one of my kinematics equations? Now, if I look at my kinematics equations, I'll notice that they all have a in them, right? And so that's good because I'm looking for a. But the other thing I notice when I look at my kinematics is that all of them either have my final velocity or they have time. So without those, without one of those, I'm not going to be able to use my kinematics equations to determine the acceleration of the block. So instead, I'm going to have to say, okay, well, that was a nice thought, but I'm going to go ahead and use dynamics instead. Now, as you do these problems, you will get more and more comfortable with, oh, in this situation, I need to use such and such. In this situation, because you'll be able to see what is there and what's missing. Right now, I'm trying to model that idea so that we can say, well, why are we choosing the method that we're choosing? Which in this case would be Newton's second law. So I am going to do a free body diagram because that's what I should do with forces. You have the normal force, which is perpendicular to the ramp, and then you have the force of gravity, which is straight down. And remember, we talked about in class how that angle right there, the angle of the ramp, is the same as this angle right here. All right, so that's 15 degrees because we started with our y-axis here and we rotated everything over 15 degrees so that we could get our x-axis there. So that's 15 degrees. All right, so now I'm really interested in the horizontal direction. Okay, in class we did both the horizontal and the vertical. Right now I'm just going to go ahead and start with the horizontal. All right, because I'm recognizing that that's probably the most valid information. If I need to later, I can go ahead and write the vertical. If I write the horizontal and it doesn't give me what I need, I'll go write the vertical then. But for now, in this question, to keep the video a little shorter, we're just going to start with horizontal. All right? So we're going to go sum of the forces equals MA. And we are going horizontal, so I'll put the little X's down there to remind me. So what horizontal forces do we have? Well, you'll notice that because there's no friction, there's no tension or any of those other things on there, the only horizontal force I have is this one, the horizontal component of gravity, which is very small. Remember, the right angle needs to be between your vertical and your horizontal there. The horizontal is parallel to the new horizontal. It's not parallel to the ground. Okay, so that one right there, so that is opposite my 15-degree angle. So therefore, that horizontal piece right there is going to be FG. Opposite will be sine theta. All right, which theta is 15. All right, they don't actually give me the mass, so we'll see from there what we can do. So sum of the forces, the only force is going to be, and remember I told you in class that sometimes we freak out a little bit because I'm like, I'm gonna need the mass for the gravity. Don't worry. Let's see where it goes. All right, so that would be FG sine theta. Now, sorry, this should be a subscript. This is not F times G, it's a subscript G. Times sine of theta, that's this, should be equal to the mass times the acceleration. All right, now Fg, we've learned that the force of gravity is the object's mass times the gravitational field strength, or the acceleration due to gravity. So that's G. So we go mg sine of theta equals ma. And you'll notice now, what do you see with the masses, right? In fact, the last question here, which I didn't write up on the board, I was going to talk about at the end, but why not now? The last question was, can we show that it doesn't matter what the mass of the block is, that I'm going to get the same thing in either way? And yes, in fact, that's what we're doing right now, right? We see that the mass on this side and the mass on that side are going to cancel out. You just divide by m. M goes away. M really doesn't matter in this particular situation, right? And so we have G, which is 9.8 sine of 15 equals AX, and then I just plug it into my calculator. Remember, this is positive 9.8 if I have defined positive to be down my ramp, which I usually like to do that because I know that's the direction my object's going. So I'm going to go 9.8 times sine of 15. I am going to make sure I'm in degrees, not radians. Okay, and when I push enter, I get 2.536. So I'm just going to go 2.5 because it does look like I have two sig figs there. I only wrote down one there, but that's fine. So 2.5 meters per second squared equals AX. So you'll notice I was able to figure out the acceleration. Nice, right? Yeah. So we got the acceleration there, 2.5. That doesn't show up very well on the screen. I said it, but there we go. 2.5 meters per second squared. Okay, so that's part A, and technically part C, because in part C I was gonna just again mention, does mass matter? And the answer is no, mass does not matter, Mr. Bauer. It really doesn't. See, yep, right there. So you can just point to this part and say, look, mass is canceled out, mass doesn't matter. Okay, the second part of this is that it wants us to find the speed at the bottom of the incline. Now, you may have thought, well, Mr. Bauer, you wasted all that time writing out that table, and we didn't even use that. Well, guess what? We're going to use it now, right? Because now it's asking for my speed, it's asking for my velocity. The speed at the bottom of the incline, I think I need a new color. Hold on. Here we go. The speed at the bottom of the incline, that's that V right there. That's that V right there. That's what we're going to solve for. So doing this did not waste any time, right? In fact, I know my acceleration now. I just found it. My acceleration was 2.5. So now I can pick out my kinematics equation. Now the kinematics equation I'm going to use is the one that does not have t in it. Notice that I don't have t and I'm not looking for t. I don't have v, but I am looking for it. So I need to make sure v is in there. So I'm going to choose the equation that does not have t. And if you look at your kinematics equations, you should see v squared equals v naught squared plus 2a x minus x naught. And so therefore we can go ahead and put those numbers in. So we'll go v squared equals v naught squared, which was 0, plus 2 times a, which is 2.5, times x minus x naught, so that would be 2 minus 0. And from there you can put it in your calculator, say, Mr. Calculator, what's the answer? And we go 2 times 2.5 times another 2, and I get 10. So v squared equals 10. Now I do need to square root that, and I'm going to get 3.2. So v equals 3.2 meters per second. There you go. So hopefully that was a nice example for you how we can combine these ideas of the Newton's laws, Newton's second law specifically, with acceleration and forces, and the kinematics to help us get an answer. All right? So we'll try to do more of that as we go forward, but for now, that's a good start. We'll see you next time.